In this video, we are going to learn about antiderivatives and how to find them. So for example, antiderivatives, where you would use this in a situation is, for example, let's say you have the velocity of a particle, but you actually wanted to know its original position at a certain time. Or let's say you know the rate that a water was leaking from a tank and you wanted to know the amount leaked over a specific time. Or again, if you know the rate bacteria is increasing, but you want to know what the size will be at a specific time in the future. So an antiderivative, if f is an antiderivative of a function on an interval, then the most general antiderivative of f is going to be capital F of x plus c, where c is an arbitrary constant. So basically what this means is an antiderivative and a derivative would actually be, it's like going in reverse order, for example. If I have x cubed plus 2 and I want to take the derivative of it, the derivative would be 3x squared. If I want to take x cubed minus 3 and take the derivative, I would still get 3x squared. X cubed plus 3, same thing. If I took the derivative, I'll get 3x squared. And then if I had even x cubed, again, all of these would give me 3x squared when I want to take the derivative. So if I started with 3x squared and I wanted to know what was my original, that is where I'm going to take the antiderivative. Or what we're going to talk about later is another term, is the integral of that function to figure out what was your original function. So for example, if you're trying to think in reverse, if the derivative was cosine, then what was the original function? And the original function would have been sine, because the derivative of sine is cosine. So you got to think of what made the derivative to get you to cosine. And so the answer would have been sine. For example, if the derivative is x squared, then what was the original function? Well, if the derivative is x squared, that means the original function had to have been a cube. Because when you take the derivative of a cube, you throw it in front and you subtract 1, and that's how I got my square. But if it's a 1x squared, I got to figure out, well, if I take the derivative of x cubed, I would get a 3x squared. But I can't have a 3, they have a 1. Which means my number in front must have been a 1/3 x cubed. Because again, if I take the derivative of this, 3 times a third cancel each other out, giving me a 1, and then I subtract 1, and that's how I get x squared. So that's how it worked. And then last, I'm trying to think of what, if I take the derivative of something, I get 1 over x. Well, the derivative of natural log of x, because again, if I was to take the derivative of natural log of x, it is actually the function 1 over x. So here is a table of the general antiderivatives based off of a function. So if you'd like to pause the video to write some of these down, we will talk about these at a later date. But the easiest one basically is e to the x, which is great because the derivative of e to the x is e to the x, which means the antiderivative is also e to the x. But I do want to show you, if you notice, there is a plus k at the end of all of these, and here's why. Let me go back up. Technically, I probably should actually say that the original function was sine of x plus some arbitrary number, c, where c is a real number. Here's why. The derivative of sine is cosine. That's why I got cosine. The derivative of a number is 0. And so what we have to assume is there is a chance that there could have been a number with this function, because the moment you take the derivative of it, it goes away, leaving you with the cosine. So again, here, it technically probably should be the function plus c. Why? Because when you take the derivative of c, you get 0, leaving you just the derivative of the first. And so the same thing at the end. The derivative should have been really plus c, because the derivative of natural log is 1 over x, and the derivative of c, the derivative of any number, is 0. So be aware that whenever you're taking the antiderivative, there technically should be a plus c, or in some instances, plus k at the end, which is why here it'd be a plus k, because again, if I take the natural log of x, it's 1 over x. If I take the derivative, So let's do a problem. A particle moves in a straight line and it has an acceleration. If you have some position of time and I take the derivative, I would get the velocity. And if I take the second derivative, I would get the acceleration. So the acceleration is the second derivative. Velocity is the first derivative. And the original was the position. So in this case, they tell us the acceleration. So I know that the acceleration was 6t plus 4. And I need to find the velocity, which means I need to go in the reverse order. What derivative will get me to 6t? Well, if it's a t, that means it becomes a square. Why? Because the derivative of t squared turned into t. But I need to figure out which number here would get me a 6 if I was to take the derivative. So 2 times what number gives me 6? And the answer is 3. Now let's check it. 3t squared, what's the derivative? It's 6t, so it worked. And if I have a number 4, that means my antiderivative was a 4t. Why? Because if you take the derivative of 4t, you get 4. And then there's actually going to be a plus c. Why? Because the derivative of a number gives me 0. That is why it wouldn't be in the acceleration, but it could have been the velocity. And then here's what they do. They actually tell us how to find c. They tell us that the initial velocity, meaning v of 0, is -6. So I know that my initial velocity, if I plug in 0 for t, I should get the answer -6. So I'm going to do that now. So if I plug in 0, then I should let it be equal to -6. So it'd be 3 0 squared plus 4 times 0 plus c, which means c equals -6. Therefore, my actual velocity becomes 3t squared plus 4t minus 6. That is my velocity. And now they're going to tell us some more information about the position, so different color. Now I'm looking for the position. Now we know that velocity is the derivative of position, so now we got to work in reverse order. So if this is a t squared, I know my position was a t cubed, because when you take the derivative, you get t squared. And I have a number in front of 3, so I think I actually just get t cubed. Yes, because when I take the derivative of t cubed, I actually get 3t squared. So that's perfect. Now, 4t, since that is a t, that means my position was a t squared. Again, why? Because the derivative of t squared would give you t. And if that becomes a 4, I need to figure out what number should be here. So 2 times what number gives me 4? And the answer is 2. And then try it. Take the derivative. 2t squared, the derivative of 2t squared is going to be 4t, so it worked. The number automatically means it was 6t, negative 6t. Why? Because the derivative of negative 6t is just negative 6. And then we do the plus c. And then they tell us how to find c. If I plug in 0 for t, it should equal 9. So I'm going to plug in 0. And therefore, c equals 9. So that means my position was t cubed plus 2t squared minus 6t plus 9. And you can check your work now. If you take the derivative of the position, do you get this velocity? So t cubed becomes 3t squared. That worked. 2t squared becomes 4t. Yes, that worked. Negative 6t becomes negative 6. That worked. And the derivative of 9 is 0, which is why it's not there. And those are going to be your answers. Next, a ball is thrown upward with a speed of 48 feet per second. Okay, think of that as velocity. From the edge of a cliff 432 feet above. Okay, that is going to be some type of position. Find its height above the ground 2 seconds later, when's it reach max and when's it hit the ground. So first we need to think physics. When an object is near the surface of Earth, it is subject to gravitational force that produces a downward acceleration. For motion close to the ground, we assume it's a constant 9.8 meters per second squared or 32 feet per second squared. Because our units are in feet, then we're going to deal with 32. But here's the deal. You got to think of it being a downward acceleration. So therefore, the constant downward acceleration is going to be a negative 32. That is actually the function for acceleration. Because again, it is a downward acceleration. Here's one reason to look at why the acceleration should be a negative 32. If you were to graph this function, you're starting at a cliff that's at about 432, and you're throwing a ball upward, and then it's going to fall to the ground. This is concave down all the way. Concave down is when the second derivative is negative. So that is the reason I know that my acceleration is going to be a negative 32. Now, if my acceleration is negative 32, I now need to find my velocity. Now, remember, velocity is going to be basically the antiderivative acceleration. So basically, what function is going to give me negative 32 when I take the derivative? Well, first, I know it's going to be First, I know it is going to be a negative 32t. Why? Because the derivative of negative 32t is negative 32. But don't forget, there could have been an arbitrary number because when you take the derivative of it, it gave you 0. Now, we also know that the initial velocity was 48. So we are going to take this from our word problem, and I'm going to set it equal to 48 when I plug in 0, which means c was 48, which means I now know that my velocity was negative 32t plus 48. Now I can be able to deal with my position. So I got to go in reverse order again. I need to figure out what function that when I take the derivative, I get negative 32t plus 48. Well, if that's a t, then I know it is going to become a t squared. Why? Because the derivative of t squared is something t. Now I got to figure out what that number is. I know when I take the derivative, I multiply the 2 by whatever is there. So I got to figure out 2 times what number gives me a negative 32, and that's a negative 16. And take the derivative of this, and you do get negative 32t. And then if that's plus 48, then it would have been a positive 48t. And then again, do not forget the arbitrary c. But I know that at my initial time, at the very beginning, right before I throw that ball, I am already 432 feet in the air. So I'm going to set 432 equal to negative 16 times 0 squared plus 48 times 0 plus c. So I know that c is 432. So now I can tell you that my original position was negative 16t squared plus 48t plus 432. Next, they want to know about the max height. Okay, that is a clue. Maximum is dealing with the first derivative, basically when the first derivative is 0. Well, in this case, the first derivative is the velocity. So I'm going to take the velocity and I'm going to set it equal to 0. And I'll get 1.5. And now I got to plug that back in to the original function, which is my position. So I'm going to take and I will get 468, and in this case it's feet. That is my max height that it will reach is 468 feet. When does it hit the ground? It hits the ground when the position is set equal to 0. So now I'm going to take the position and I'm going to set it equal to 0. And I'm going to solve. And the best way to do that is either to graph or do quadratic formula. So you can either graph it or the quadratic formula in this case to find the zeros. It would be negative 16x squared plus 48x plus 432. Okay, if I graph, well, it shows me right there. I'm still going to go back to Zoom 6, and I can see that it crosses in two places. We don't care about the negative because you can't have negative time, so we only care about the positive. So I'm going to hit second, trace, and I'm going to go to the 0. I am going to go, I'm looking when my y values are getting close to 0. That's how I know that I'm getting close. I'm at 40. Ooh, all right. 15 is when it's up here somewhere. And then I go to negative 10 down here. So that must be my left bound, hit enter. My right bound where I went negative, enter, enter, and it's at 6.91. And it would have been seconds. So it actually hit the ground 6.91 seconds after it got thrown. For some practice, let's try to attempt to find the antiderivatives of these functions. So here's how I would go through it. Or try these on your own and then resume the video to see the answers. Okay, so if this is my derivative, then I'm going to make it a capital F to show the antiderivative. If that's a cube, then I know that my original function was a fourth. Now, I got to figure out 4 times what gives me 2. So it would have been a half. 4 times a half is how I got 2. And then a minus. Since that's an x squared, then I know the original function was a cube. And now again, I got to figure out 3 times what number gives me negative, well, not negative, 3 times what number gives me 2/3. 3 times what number gives me 2/3. So if you think of cross multiplying, 3 times 3 is 9 times my number equals 2, which means I now divide by 9, which means I get 2/9. Now let's take the derivative and make sure it works. 3 times 2/9 gives me 2/3. Yes, it worked. Okay. So that is how I found 1/2, because 4 times a half gave me 2. 3 times 2/9 gave me 2/3. And now last, it's a plus. And if that's an x, that means it was an x squared. And 2 times what number gave me 4? And it's 2. Because 2 times 2 gave me 4. And then again, because we did the antiderivative, there is a plus c. Next, okay, think of this as 3 times x to the 1/2. Okay, so to do the antiderivative, I got to figure out x to the what when I subtract 1 gave me 1/2, which means it's 3/2. Because if I take the derivative of x to the 3/2, I would get 3/2, and then x to the 1/2. That's how I got 1/2, so it worked. And now I got to figure out 3/2 times what gave me 3. No, it would have been 2. 3 times a half, sorry, 3/2 times 2 gave me 3. Let's see if that works. 3/2 times 2, yes, the 2's cancel, leaving me 3. So that's how I got a 2 in order to get my 3. Now, this was a minus 2x to the 1/3 because that's a cube root. So now I got to think, if that was a cube root and I had to subtract 1 to get it, then this must have been 4/3 because 4/3 minus 1 gave me 1/3. Okay. Now, I need to get 4/3. When I multiply it by whatever this is, I have to get a 2. So 4/3 times what number gave me 2? So if I cross multiply, I will get 4 times a question mark equals 6. So divide by 4 and I get 3. So this would have been 3/2. Now let's check that. 4/3 times 3/2, the 3's cancel for over 2, is 2, so it did work. And then plus c. So you can leave it like this, or you could have put it back in to a radical form. Either one would have worked. And last, I'm trying to figure out what, when I take the derivative of, will get me 1/5. Well, thankfully, 1/5 is a constant, which means it's going to be 1/5 x. That's the easy part. This one is a negative 2 over x. So think of it as negative 2 times 1 over x. And the derivative of natural log of x is what gave me 1 over x, because the derivative of natural log is 1 over x. And don't forget your plus c. So let's try one. A particle moves with a velocity. We're only dealing with positive time. The particle is at position -6 at time t. So basically think of it as the position at time being 2 is -6. And now we know the velocity, we're going to find the position. So if the velocity is this, think of this as the first derivative. So the original function, if this was 6t squared, that means the original function is a t cubed. And now I got to figure out, what should this number be? 3 times what number gave me 6? And the answer is 2. And then plus 19 means it's going to be plus 19t. And then don't forget the c. And now we're going to plug in this. So I'm going to set this equal to -6 everywhere t is equal to 2. 54 plus c. So I'm going to subtract 54 and I get -60. So therefore I know that my position is 2t cubed plus 19t minus 60. And now they want to know, what is the position at 0? Then the position at 0 is going to be -60. I guess I don't have to do all that. We already found it. It's -60. Now, we are going to attempt to graph this. Let's assume that this is the derivative. So anywhere the derivative is below the x-axis, the original function is decreasing. So I know that the original function is decreasing to about there. Well, let's say if that's 1, 2, 3, 4, 5. So until about 2, it's decreasing. And then anywhere it's above the x-axis, that means the original function is increasing. So from 2 to 3, it's increasing. And then from 3 to 4 to 5, it is decreasing again. Now we're going to look at, if this is the derivative, we're now looking at concavity. So the derivative, since this is a derivative, anywhere it is decreasing, it's going to be concave down. So therefore, instead of it being a straight line, it is actually concave down to 1. So we're looking at a concave down. And then from 1 to 2.5, it is increasing, which means it becomes concave up. So from here to about 2.5, it's concave up. And then from about 2.5 to 3.5, it's concave down. And then from about 3.5 on, it's concave up. So this becomes my very, very ugly graph. So it was decreasing to 2, increasing to 3, decreasing the rest. We got that. And then concavity changed it. It was concave down to 1, concave up to 2.5, concave down to about 3.5, and then concave up. So therefore, our final should look something like this.